All right, so we are going to talk about the chemical bonds. Alex, do you mind just turning off? It's the second light switch, the one closest to the door. Right, so this should go right along with your notes. We're recapping chemical bonds. So we're going to talk about ionic bonds, covalent bonds, van der Waals, and then we're going to spend extra time on hydrogen bonds because that leads us into the properties of water. So one thing that we learned is that reactions, electrons, it should say, electrons form chemical bonds. So compounds are held together with the electrons. Remember we learned what's the important thing about valence electrons? Why are they important? They're important because they form chemical bonds. That's why we took so much time drawing atoms, figuring out how many valence electrons they have. And then we learned that they all want that full outer valence. So they'll interact with each other. They'll trade and give and share electrons to get that full outer orbit. And then they're happy. And that's how bonds are formed. That's how chemical bonds are formed. So valence electrons are involved in forming those chemical bonds. So we're going to talk about each type of chemical bond. The first one is an ionic bond. If it's going to change for me. Nope. There. So ionic bonds are formed when we form ions first. And if you guys remember, an ion is an atom that has lost or gained electrons. So an atom that's gained or lost electrons is an ion. And since they're no longer balanced, they have a charge. So sodium, in its natural state, is completely balanced. It has the same number of protons as electrons. So it has the same number of positive charges as negative charges. Chlorine is the same way, except here's what happens. Sodium only has one valence electron. So it wants to get rid of that electron. Can you close that, Josh? Thank you. It wants to get rid of that electron so that it has a full outer valence in the next level down. And remember, we talked about this too. I asked them questions. It's much easier to give away one electron than try to get 7. And so chlorine has the opposite problem. It has 7 electrons in its outer valence. It needs one more to fill that valence. And it's much easier to find one than it is to give away 7. We always want to work with the smallest number of electrons. The fewer number of electrons we can move around, the better. So it would rather take on an extra electron. Well, when sodium gives away, right here, when sodium gives away an electron, it becomes positive. And when chlorine gains an electron, it becomes more negative. Oops. It's not going to work for me. So this is explaining how an ionic bond is formed. First, an atom loses electrons. If you lose a negative charge, you become more positive. So first, an atom loses an electron and becomes positive, and then another atom gains an electron, takes on more negativity. So it becomes negative. Then those opposite charges, sodium now carrying a positive charge, chlorine now carrying a negative charge, that's what attracts them to each other, kind of like magnets. So they're ions, each carrying a charge, because they gave away and took electrons. Now that opposite charge pulls them together. And that's what an ionic bond is. So we've described an ionic bond. It's a bond in which electrons are given away and taken. An ion is an atom that has gained or lost electrons. It has a charge. And that when we create those ions are attracted to each other, and that forms an ionic bond. Do you guys remember when covalent bonds are formed? What's a covalent bond? Do you remember what co means in front of the word? To share. So covalent bonds form when they're sharing electrons. And that usually is shown by showing more than one atom together kind of sharing that outer orbit. Where if we go back here, we see that we're watching sodium give away an electron to chlorine. So this is what an ionic bond looks like. But when they're sharing in that outer valence, that's what a covalent bond looks like because they're sharing. And sharing allows the atom to attain a full outer valence. So here, let's see, what would we have? 1, 2, 3, 4, 5, 6. 6 would be carbon. So that would be a carbon dioxide, 2 oxygens. Carbon shares 2 electrons with this oxygen and shares 2 electrons with this oxygen, fills its outer orbit. So when we see them like this, sharing that outer orbit, that's a covalent bond. And the next question asks us, this is a pretty good question, how many covalent bonds can an atom form? And that's just as many as it needs. In other words, if it needs 3 electrons, it can form 3 covalent bonds. If it needs 4 electrons, it can form 4 covalent bonds. So if we look here, nitrogen has 1, 2, 3, 4, 5 of its own electrons. So it needs 3 more to be at 8 and be happy. So hydrogen forms 3 covalent bonds, fills in those 3 missing. And then each of those hydrogens is now happy because hydrogen has that weird valence where it's just the first one. Remember, that first one fills up at 2. So now hydrogen has the 2 it needs. Nitrogen has the 3 it needs. They're sharing those electrons and the valences are full. Down here, carbon needs 4 electrons to fill its outer orbit. So it can form 4 different covalent bonds. And then we learned about van der Waals. So van der Waals is that slight attraction between molecules that can develop between oppositely charged areas of an atom. So one atom is going to have oppositely charged areas. And I'm just going to show you in a drawing, the same drawing that I had done the other day, where if we've got one atom, and remember the orbit is part of the atom, but the nucleus is here with its positive protons, and this outer line represents the orbit. So out here, we'd have our negative electron, and actually it's orbiting like this, right? But it creates in this one atom kind of a positively charged area and a negatively charged area. And van der Waals only works if there's like lots and lots and lots of molecules. So you have to have lots of surface area. And they have to be really close to each other. Remember how even the fingerprints on our hand create such a mountain ridge that we can't get close enough to something to make our hand stick? So we're talking on a very, very small, small, small scale. But if we get those atoms close enough to each other, the orbit of another atom might have the nucleus down here with its positive protons, and the electrons orbiting, and this attraction between the different areas of an atom is called van der Waals attraction. And that's how geckos climb walls. All right, and before we go any further, we're going to review hydrogen bonding and start talking. We're just going to talk about a few of the properties, two of the properties today, really. But we need to talk about chemical reactions. So chemical reactions occur when molecules become rearranged, as existing bonds break and new bonds are formed. So here we've got the example of photosynthesis. We're taking carbon dioxide and water and we're creating glucose and oxygen out of it. We're going to take 6 of these molecules of carbon dioxide, and then we're going to break them apart. We're going to break those bonds. We're breaking apart the atoms. And then we're going to take this water. This is what a plant does. This is literally what a plant does. It takes in the carbon dioxide from the air. It breaks apart that carbon dioxide into atoms. It takes up water from the ground, and it breaks those bonds. It breaks apart the water into its individual atoms. It rearranges them and puts them back together as glucose, which is sugar. That's the food that plants use. And oxygen, which is what plants give off, right? So this is a chemical reaction. And we need to remember that these are the reactants on the left-hand side, and these are the products. And we don't use an equal sign there because they aren't the same. This arrow tells us that we're taking the reactants and we're changing them into different products. So here, in this reaction, reactants, or the starting materials, are carbon dioxide and water. And the products, or ending materials, are glucose and oxygen. Now, just to prove to you how this works, that we aren't creating, you think in chemical reactions, let's say you, when you put vinegar and baking soda together, and then it creates all those bubbles and, the volcanoes of elementary school, you know what I'm talking about? Yeah. That happens solely because we're rearranging the atoms and creating something different. So I'm just going to show you, using this chemical formula, I'm going to show you how we don't gain or lose electrons, they just rearrange themselves. So you have to agree with me first, just looking at it, that carbon dioxide and water is completely different from sugar and oxygen, right? They aren't the same thing. So we start with 6 carbon dioxides. That's 6 CO2s, which means that we've got 6 carbons, right? And then since there's 2 oxygens in every molecule, and we have 6 molecules, that means that we have 12 oxygens. Okay? We have 6 waters, which means that we have 12 hydrogens, because there's 2 hydrogens in every water molecule, so we've got 12 hydrogens. And there's only 1 oxygen in each one, so we have 6 oxygen. In the next one, we have 6 carbons, 12 hydrogens, and 6 oxygen. And in the last part, oxygen molecules don't like to be alone in nature. If they aren't bound to other atoms, they stick to each other. So when it leaves the plant, it's actually as O2, 2 oxygen molecules stuck together. And if we have 6 of these, it means we have a total of 12 oxygen. Now we can go back and cross them off. They're equal, right? Here we've got 6 carbons that we started with, 6 carbons that we ended with. 12 oxygens that we started with, 12 oxygens that we ended with. 12 hydrogens that we started with, 12 hydrogens that we ended with, 6 oxygens, 6 oxygens. In other words, literally, we just broke apart those atoms and rebuilt them into new materials. It's kind of like going into preschool. And Billy had just built a castle out of Legos. And you go over and you tear apart every Lego and you rebuild it into a bridge. You didn't destroy any Legos. You didn't throw any Legos away. You just tore it apart and rebuilt it. And that's what a chemical reaction really is. All right, so in this picture, does the compound pictured here, does this show a covalent bond or an ionic bond? It's a covalent because we're watching them shared here. Otherwise, we would see them being given away. What's the importance of valence electrons? You guys remember? Why did we learn about valence electrons? They form bonds. Yep. They form bonds. That's why we spent so much time learning about the valence electrons, because they're so important in forming bonds. Okay, we're going to go through a little bit of the properties of water. We're not going to go all the way through this. We'll finish it tomorrow. But before we get going, this all happens because of hydrogen bonds. And hydrogen bonds happen because water is polar. So these are things that we need to recap, review. Please let me know you're watching. Thank you. All right. A polar molecule is one in which the charges are uneven. And in water, it's because of partial charges. Remember we learned that symbol for partial? But like sodium chloride, if you remember, sodium chloride, NaCl, that's also a polar molecule because sodium carries a positive charge and chlorine carries a negative charge. So it has opposite charges. That makes it also a polar molecule. In water, though, we need to remember, and we talked about this before, that the negative pole is near the oxygen. So the oxygen carries that partially negative charge. And the positive pole is between the hydrogen atoms. And literally, an oxygen atom does arrange itself almost in this like V-like shape, where the hydrogens kind of congregate on one side, sort of the oxygen molecule. So that creates this area up here to be negative, and this area down here to be positive, or partially positive and partially negative. So it's polar. Remember, think about the poles of the Earth. You guys know that the Earth has magnetism, right? We have magnetic fields on our planet. And that has to do with the North Pole and the South Pole having opposite charges. So it forms magnetic fields between the two poles. So that's where we get that idea of poles. One end being positive, one end being negative. So hydrogen bonds are formed between water molecules. In other words, they're formed between that partially positive hydrogen atom and the partially negative oxygen atom. And this is review. We learned this on Friday. So hydrogen bonds form between water molecules. This bond here that holds the water molecule together, that's covalent. That's a strong bond. We're not talking about how we hold one molecule together. We're talking about how many water molecules stick to each other, which is why that drop of water stuck to my finger on Friday. It'll just hang there because those water molecules will pull together because of this partial charge, because it's polar, like a magnetic attraction to different parts of the molecule. So here are the properties of water that we're going to discuss. Today we're just going to go through cohesion and adhesion. That's how water sticks to itself, but water, because it's polar, will also stick to other molecules. So when water was dangling like a drop off my finger, it was sticking to my finger, right? It had to stick to my finger in order to hang there. That's adhesion. But it wasn't just one or two atoms that were sticking to my finger, it was a whole drop. And those drops, that drop was full of hundreds of atoms that were clinging to each other too. So when water sticks to itself, it's cohesion. We'll also learn that specific heat capacity. This just means that water has the ability to hold a lot of heat. And that is because of all of the hydrogen bonds that form between the molecules. So we're going to learn why that happens, how that happens. And I know you guys have learned this before, but we're going to learn why this year in here, why ice floats, because that's an anomaly. Normally in nature, the solid form of a molecule will sink in the liquid form, and yet ice floats. How can it be less dense as a solid? So we're going to learn why that happens, how that happens. And then also, because water is polar, it's really good at dissolving things. It's called a universal solvent, meaning it dissolves. Water will dissolve more things than the strongest acid any scientist has ever made. All right, cohesion and adhesion. This is what we're going to talk about today, and then we'll save the rest for tomorrow. Cohesion is the attraction between molecules of the same substance. So think about co-workers. They work in the same company. Co-captains play for the same team. Co in front of it is telling us that it's an attraction between the same molecules. So when water is attracted to water, that's cohesion. But water will also attract to unlike molecules or other molecules, and that's adhesion. Kind of like the water molecule stuck to my finger. It was attracted to the molecules in my finger. And that's adhesion. I always think of adhesive. Adhesive is like tape. We use tape to stick things together, and they don't always have to be the same. We can stick tape to a wall. Or we can stick paper to a wall using tape, using an adhesive. Adhesives stick unlike things together. Cohesion is the same. So when we put cohesion and adhesion together, you can come up with something called capillary action. And this only happens in tube-like structures. So in plants, this is how plants take water up from the roots to the leaves. It's through capillary action. Capillary action only happens because of adhesion and cohesion. It needs both or it won't happen. And what happens is you see the water molecules attracted to the sides of the stem on the inside. I'm going to change color so you can see it. So those water molecules are attracted to the side of the tube. And as these water molecules keep reaching for the side of the tube, they're also pulling on the water molecules down below. So as one reaches for the side of the stem on the inside, it's also holding on and pulling up all the other water molecules that are close to it. And so that's how water is pulled up through the stem of a plant. It's through capillary action. And capillary action only happens because of adhesion and cohesion. Adhesion between the water molecules and the walls, and then cohesion between all of the other water molecules, pulling up the rest of the water molecules up with it. And together the water will rise all the way up through the stem. And that's called capillary action. Oh, I lied. We're going to talk about surface tension too, and then we're going to be done. Surface tension. So you guys have seen how a bug can walk on water? Or sometimes a leaf. Sometimes the reason that a leaf floats on water is because of its shape. It takes on a boat-like shape. But water, because those water molecules on the surface have all those hydrogen bonds pulling it together, it creates like this artificial surface that you can float things on, that it'll support on top of it. Something can be put on top of those water molecules without breaking the hydrogen bonds. And when we do our water investigation on Wednesday, you guys are going to see that you can actually float a paperclip on water because of surface tension. It's not easy to do, but you can do it. And that's because all those tiny little water molecules are pulling together to create this tight surface. I always think of, do you guys ever play Red Rover when you were little? Red Rover, send Alex right over. Well, when I was little, they'd always call on me because I was little. And you'd see this line of people holding hands, and I would come running as hard as I could, and I could never break through anybody's hands. I would jump and I would just all out, and I couldn't break anybody's hands. And you can kind of think of surface tension as a bunch of water molecules holding hands to the point where they can hold things up. Now, obviously something heavy is going to break those hydrogen bonds. That's not that strong of a bond. That's why we aren't walking on water, because we're too heavy. We break those hydrogen bonds. But a paperclip or a small bug like this doesn't break those hydrogen bonds, and it creates surface tension. So, let's review. Where are hydrogen bonds formed? Do you remember? Where are they formed? No, where are the hydrogen bonds formed? Where do we see hydrogen bonds? Between water molecules, right? And you can change this big answer and just say between water molecules. So hydrogen bonds are formed between water molecules. And then we're going to talk about specific heat capacity, water's ability to take on a lot of heat. It can hold or store a lot of heat because of its hydrogen bonds also. Come on, move for me, please.